Okay, so the substitution, the UV substitutions are going to be given because they're not easy to come up with in a similar way that you were given, say, the integral of, what's that? E to the 1 over x, for instance, right? So then you would have this over x squared to dx, right? You do the derivative of 1 over x, the derivative is negative 1 over x squared, which you have in a way. You would just need to compensate with a negative, right? Or if you have the integral of, say, 4x to the 4th minus 3x, then, now let me do x squared, for instance, plus 1, and then typically you would have something like, what is that, times 16 x cubed plus 2x dx, right? So it's easy to see the pattern u dg, right? However, when it comes to integrals with double integrals, that pattern is not easy to see, although there's guidelines to help us, so we can see the region of integration, so we can see the nature of the integrand and the like, but at least the way this textbook works, it gives us the substitutions for us. Other textbooks, you're on your own. Look at the integrals, you figure out the UV substitution, which is, again, it's not easy. All right? Okay, so let's see. Let's evaluate. Oh, what else do we do? So we're given the UV substitutions, and then sketch the original region of integration that is R in the xy plane. And then we will do some algebraic work and get the new region of integration in the world of u and v. All right? So what are we going to do? In a similar way, we change the limits of integration. You remember how I always did u of 0, u of 4. Well, in this case, we're going to change order pairs, not just numbers. So you'll see how it's going to work. Then what else? Compute the Jacobian, because that's the compensation factor that is the compensation factor for the UV substitution. And, well, change the variables and evaluate the new integral, which typically is going to be an easier one to evaluate. Okay, so evaluate the integral 4x dA, where R is the square region with vertices at the origin and those other 3 points. And they're giving us the substitutions: x equals u plus v and y equals to u minus v. So we don't have to figure out the uv substitutions. Okay, so number 1. Okay. So number 1, determine the appropriate substitutions. Well, again, we're given those substitutions, but I'm going to write them again because I will need to do some algebra to this later. U plus v and y equals u minus v. So number 2, sketch the region. So I'm going to sketch the region given by these points. Okay. So what are these points anyway? So number 1, that's the origin. What else? We have the point 2, 2, which I'm going to represent it with this point. We have the point 4, 0, and we have the point 2, what's that? Negative 2. All right? Let me connect the dots with diagonal lines. Okay? And of course, shade the region of integration. Okay? Now, think about this region of integration. Do you like that region of integration? So, why not? Why it's not the best region of integration? Why not? It's tilted, right? And yes. Okay, let's think about it. Is this region vertically simple? He said yes. Some of you say yes. That is okay. Do we have? And so for every vertical line I trace, do I always have the line with the positive slope at the top of the diagonal line with negative slope? No, right? So there is a point where the slopes kind of interchange and it's no longer a vertically simple region. Is it horizontally simple? Same situation, right? So without knowing anything about the Jacobian, we will be screwed. Why? Because regardless of whether you set up the double integral as vertically simple or horizontally simple, you would have to set up two double integrals, one for this part and another one for this one. All right? So, or if you're clever, how about just find the area of this one? Or rather, integrate over this region and then multiply by 4. However, that would not be a valid move because look at this function, 4x, right? That would represent the roof of a solid, right? So, what do you know about the symmetry of 4x? 4x, what is that? It's like this diagonal here. Well, it's going to be a plane, and it's not perfectly symmetric. And look at the position of the square. It's not symmetric to the origin either. So we cannot just find the area of 1/4 of the square and then multiply by 4. So I mean, integrate over that part and multiply by 4. That would be an incorrect result. So that's why we do the Jacobian. All right. So. Okay, let me write down the equations for each of these lines. Okay, so that is y equals to x, that is y equals to negative x, that's y equals to x minus 4, and this is y equals to x plus 4, right? Okay, what are we going to do now? Well, number one, let's use the substitutions x and y. For x and y in terms of view, I'm going to think of these two equations as a system of equations. So I would like to solve for u and v in terms of x, because what are we given? So we're given x in terms of u and v. That's to convert those points from one world to the other. But we need these equivalents to go in the backwards direction, from the world of u and v to the world of x and y. Right? So I'm going to solve for you for the first equation. That is u equals to x minus v, all right? And I'm going to solve for v on the second equation. So that is negative v equals to y minus u, and v equals to u minus y. How about that? All right? Why am I doing this? Because, check this out, I will substitute u over here, okay? That'll be u equals to x minus the quantity v, which is u minus y. That is u equals to x minus u plus y, and I'm going to move the u's to the left hand side, so that's 2u equals to x plus y, and what do we have? U equals to x plus y over 2. Isn't that an equation for u in terms of x, y rather than x in terms of u and v? So in a similar way, I need to obtain another relation for v in terms of x and y. All right? So I'm going to back substitute this v over here, okay? Because this u equals x plus y over 2, I'm going to substitute it there. All right? I'm going to substitute it there. So that'll be then v equals to u, which is x plus y, over 2 minus y. So I need common factors. So do you guys agree then that this is y over 2 times 2? Yep. We can write everything in one single quotient. V equals to x plus y minus 2y. Everything over 2. And simplify the numerator. That's x minus y over 2. So we have the two relations to go from the world of x to the world from the world of x, y to the world of u and v, and also the expression to go from the world of u, v back to the world of x, y. All right? So we need to go both directions. What are we going to do here? Okay. Remember how we did the integral e to the x squared dx? X, okay, so u equals x squared, du equals 2x dx, and then x dx equals 1/2 du. So what are we doing? We're going from the world of x to the world of u. That's what we did with this system of equations. And then when we integrate from 0 to 3, for instance, I'm going u of 0, u of 3. That is 0 squared, which is 0, and 3 squared, which is 9. So now we need to look at the equivalent points in the world of x, y. What are their equivalences in the world of u and v? Okay, so let me call this set R. Okay, so this is our set R. So R, which is all order pairs x, y that we're given, and we're going to take those points to the world of S, which is the world of u and v. Alright? What did we do with that single integral? Didn't we substitute the original limits 0 to 3 in our u expression? Right? Okay, so we're going to substitute these 4 order pairs in our u and v expressions in terms of both x and y, right? So we're doing essentially the same, but rather than converting values of x which are the limits of integration or the interval of integration, we're changing order pairs. Okay, so the point 0, 0, check this out, how we're going to do this. 0, 0 for you. Okay, 0, 0 will be, 0, 0, 2, 2, what else? 4, 0, and 2, negative 2. Okay, 0, 0. Okay, what is u? 0 plus 0, isn't that 0? Divide that by 2, it's still 0. That's u. Okay, what about v? 0 minus 0, that's still 0. Divided by 2, that's 2. I mean 0. What about the point 2, 2, the second point? So what's the u related to this point? Okay, so 2 plus 2, isn't that 4? Divided by 2, that equals 2. 2 minus 2, 0. Divided by 2, 0. What about the point 4, 0? Okay, x equals 4, 4 plus 0, that's 4. Divided by 2, that's a 2. 4 minus 0, that's 4 over 2, that's 2. Okay? And lastly, what's that? 2 plus negative 2, that's 0. And 2, careful, minus negative 2, that's 2. Plus 2, which is 4. Divide that by 2, that's 2. Okay? So I'm going to use those 4 order pairs in the column of the world of S, right? To create a whole new world. Okay? So let's go from the universe of R to the universe of S. Okay? That is, I need at least a 2x2 grid or so. So that'll be 1, 2, 3, 1, 2, 3. Okay. So that's the point 0, 0. That's the point 2, 0. That's the point 2, 2. And that's the point 0, 2. Now, how do you like this region of integration, guys? Isn't that a dream come true? Right? It's a dream come true. That's Jacobi's power. That's Jacobi's power to give us that dream come true, to integrate over easy regions, easy rectangular regions. Let me call this, that's no longer R, that's actually the region S, the new world, the world of S. Okay? Now, what happened here? And we need to denote what happened here. So we went along in accordance with the transformation T. That means from the world of X, Y to the world of R, to the world of U and V. Which is essentially what we do when we integrate from rectangular to polar or rectangular to cylindrical or spherical. But we don't see it in this way. We just do the transformation of the coordinates. What else do we need to do? Number 3, we need to compute the Jacobian. Okay, so that's number 1. That's number 2, getting the region of integration. Number 3, get the Jacobian of uv, because we're going to the world of uv. That is the partial of the x equation with respect u, the partial of the x equation with respect v, oh yes, with respect v, and then the second row of the matrix, the partial of the y equation with respect u, and the partial of the y equation with respect v. Okay, we can easily find these partial derivatives, guys. So what's the partial of x with respect to u? Isn't that just 1? What's the partial of x with respect to v? That's also 1. Partial of the y equation with respect to u, that's 1. And partial of the y equation with respect to y, that's a -1. Compute the determinant. 1 times -1, that's a -1, minus 1 times 1, which is 1, that equals a -2. Okay? Alright, guys. Before setting up the double integral, there's a detail I don't think I discussed when I showed you the generic integral, the general definition of the change of variables in the new world. Okay, let me go back a couple pages for that. So unlike the one-dimensional integral, we may or may not have this coefficient, these compensation coefficients as a negatives. When it comes to double and integrals where we use the Jacobian, we need to take the absolute value of the Jacobian. Why do we have to do that? Because these double integrals and triple integrals represent volume or mass or different quantity, different physical quantity that we need to make sure they are positive, right? So if you get, like in this case, in the example we're working, we get a negative result, make it positive by taking the absolute value. So we're ready to set up the integral. Okay, so that means okay, so that is the double integral over the region R of 4x dA, that equals the double integral in the new world of S, okay, of 4 times, okay, what are we going to do with the x in a similar way that you substituted with arc cosine theta in the world of polar? Well, here we're given a relation for x, don't we? X equals to u plus v, all right, times du dv times the absolute value of the Jacobian, which is a -2. All right? And then let's iterate the integral. Okay, absolute value of -2, that's +2 times 4. Isn't that equal to 8? I'm going to write it outside. And then we will integrate u plus v, du dv. And I'm going to integrate this from 0 to 2 and from 0 to 2. Isn't that an easier integral to evaluate rather than the original one? Yes. Although otherwise you would have to set up 2 double integrals, all right, which is not going to be fun. It's doable, but not the most efficient way. And I'm just going to give you the result of this integral. The idea is to know how to set this up. I mean, you can easily evaluate this integral. At this point in time, you guys are masters in integration, right? Yes, you are. All right. Let's have a look at one more example, and then we wrap up the chapter and hopefully we start another chapter. I don't know if we're going to have time. We'll figure it out. Okay, let's evaluate another double integral. By the way, there's a couple of typos here. This 4 is not supposed to be there. And what else? 0,3. Okay. This second inequality has a typo. The code I was using had issues. That's supposed to be x less than or equal y less than or equal x plus 6. All right? So evaluate this double integral where R is this region using the substitutions x equals to 3u and y equals to 6v plus 3u. All right. So actually, here is the thing, guys. When it comes to evaluating double or triple integrals using the Jacobian, every exercise, every case is different. It's not like the other types of integrals that we just follow the substitutions and we just use our tools we learned back in calculus 1 and 2. So these are a little twisted, but well, this second example will be a lot shorter and easier. You'll see. Because, well, number one, let's plot the region of integration first, okay? And for this, I need a big graph. Because, well, y is varying between, what's that? Between y equals to x and y equals to x plus 6. I'm going to go 1, 2, 3, 4, 5, 6 with the same slope. Okay? And x is varying between 0 and 1, 2, 3. And let's shade that region of integration. All right. So that is our region R. That's our region R. Okay, I mean, yes, this region R is for sure vertically simple, right? So I don't think it should be a problem to evaluate it with section, what's that, 16.1, 16.2 technique. But if we look at this region, it wouldn't be horizontally simple. That's because, check this out, I would need to break this up into 3 regions and set up 3 double integrals, and that's no fun, isn't it? But we're still expected to work with the Jacobian to get this integral here. Alrighty. So, we're given these substitutions: x equals 3u, y equals 6v plus 3u, but we're going to get the new region, the region S, in a different way. This time, I'm not going to solve for u and v in terms of x and y, because this is so convenient in the way this problem is given. So, see this inequality here, that is, x varies between 0 and 3, and see this other integral, x varies between y varies between x and x plus 6. Check this out. This is, let me highlight, first of all, let me highlight x and x with one color and y with another color. We can easily do another substitution here. All right? It's going to simplify in a nicer way. So I'm going to substitute, what's that? X, which is 3u, varying between 0 and 3. And I'm going to solve the compound inequality by dividing the 3 sides of the inequality by 3. 0 remains 0, 3u becomes u, and 3 becomes a 1. All right? What about y right here? Okay, so first of all, x varies between, is 3u, y, that's 6v plus 3u, less than or equal 6v, x, which is 3u, plus 6. Now, do you see how the 3u's are going to get canceled on the 3 sides of the inequality? Okay, cancel out. Cancel, cancel, cancel. And that's going to leave us with a simple inequality that's 0, 6v, 6. And dividing the 3 sides of the compound inequality by 6, that's going to leave us with 0 less than or equal v less than or equal to 1. Hey, isn't that a lot easier rather than plotting the points and calculating the new point from the world of R to the world of S? That's because the way the region was given and the choices of u and v, of x and y in terms of u and v, were in a convenient way. So we saved a lot of the work. We're ready to compute the Jacobian here. J equals the partial of x with respect to u, the partial of x with respect v, the partial of y with respect u, and the partial of v with y of y with respect to v. Okay, this is v, and this is also v. Okay. Okay, the partial of the x equation with respect to u, isn't that 3? The partial of the x equation with respect to v, oh, there is no v, it's 0, right? The partial of the y equation, the one in green, with respect to u, careful, that's 3. And the partial of the y equation with respect to v, that's 6. What is that? 3 times 6 minus 0 times 3. That equals 18. And in this case, we don't need to take any absolute value because the result is positive. So we're good. All right. Let's plot the new region of integration. Okay, now let's go from the world of R to the world of S. That is, oh, this inequality tells us that we're going to go, from 0 to 1, from 0 to 1. Don't you love this region of integration better? Yes. Integrating over rectangular regions, that's always a dream come true, right? Yeah.
It's just 1 by 1.
It's a 1 by 1, that's correct. That's given by these inequalities. U varies between 0 and 1, and V varies between also 0 and 1, right? So that's the UV plane. Okay. What do we do? Are we ready? Yes, we're ready to evaluate the triple integral. So we're given, the double integral. So we're given the integral over the region R of x cubed y dA. If we were to iterate this integral, just think about it. The integral from 0 to 3 and from x to x plus 6, at first glance, it doesn't seem like the most complicated integral. But look at the limits of integration, some cubes here and there. So x cubed to y, dy dx. So you don't want to go this route despite the region of integration. It's not that complicated, and the integral is not that complicated either. So in this case, you want to do the following. So go to the world of S. That is, integrate between 0 and 1 and between 0 and 1. Okay, careful. We need to cube x. But what is x in the world of u and v? Isn't that 3u? Careful, because we need to cube both the 3 and the u. We're going to do that in a second. And then what's y? That's given, right? That's 6v plus 3. Okay. And what's next? Okay, so that's simply, multiply by 18, that is the Jacobian, du dv. Okay, and I'm not going to evaluate the integral again. You can easily cube that 3u, distribute it with 6v and the 3u right here, and the 3u, and you should get as a result 656.1. All right.